Okay, we're going to get started. Hi, good morning. I'm Shannon Kiley, staff representative for the maintenance committee here at AIST. And this webinar is to highlight the Reliability Achievement Awards from 2020. Normally, these would be presented at our specialty conference, which unfortunately had to be canceled this year. So we wanted to give them an opportunity to display their work and talk about their project that has won them these awards. So a little bit about the Reliability Achievement Award. Sorry, now my computer's frozen. It is awarded to an iron and steel producing company that has made a reliability improvement within the organization. It does recognize both the organization and the individual involved in designing, proving, and implementing a policy or practice that increases the reliability of an organization. And we do offer 3 levels: a gold, silver, and a bronze. So we have people nominate and submit their projects, and then a team of 2 to 3 volunteer auditors choose a project. They go to the plant and they audit the project. There they hear the presentation from the submitter and just go and actually look at the project. Then the auditors come back and meet collectively, and everybody discusses their projects that they audited, and using a matrix ranking system based on these certain topics, we will then decide which project was awarded the gold, the silver, and the bronze. So first up, we are going to introduce Jason Vicari. He is the senior maintenance engineer at Cleveland Cliffs, Indiana Harbor in East Chicago. He graduated from Purdue University in West Lafayette, Indiana, with a BS degree in mechanical engineering. He's a certified lubrication specialist through the Society of Tribologists and Lubrication Engineers, and is a registered professional engineer in the state of Indiana. Jason is also the winner of 3 previous AIST Reliability Achievement Awards. So Jason is on right now. He did record his presentation just in case. So I'm going to play it. And then if there's any questions, please type them in the Q&A and we will ask Jason live right after. Thanks.
Hello, my name is Jason Vicari. I'm lead maintenance engineer at Cleveland Cliffs, Indiana Harbor 80-inch hot strip mill. And I'm here today to talk about the 2020 AIST Bronze Reliability Achievement Award winning project, describing our roughing mill descale system modifications. We'll start with a picture of our pump room. We have our, as a way of background, we'll start with our roughing mill descale system. Was original equipment, started up in 1965. I have 5 pumps installed, 4 operated at any given time. The original system operated, depending on which documents you read, somewhere between 1500 and 1650 PSI, and had 13 descale stations. Many modifications have been made to the system over the last 56 years. One of those was that the pump bypass was changed from an all or nothing system to each pump having a separate line back to the inlet of the pump and a shut-off valve installed. Our headers were increased from 4 to 6 inch diameter, but the feed pipes remained at 4 inches. At some point in the past, the nozzle flows were increased, and descale stations have been eliminated over time. We are now down to 6 stations. Station is top and bottom header. So our pumps have been rebuilt by many different vendors with aftermarket parts over the years. When I first started looking into this system, pump failures occurred after short lifespans, and service time less than 1 year became common. Pump changeouts were based on catastrophic failure, not on any kind of preventive method. We had pipe washout in certain parts of the system. Our bypass valves would wash out. Our gearboxes, speed increasers would experience wiped Babbitt bearings and broken gear teeth. Our pump rebuild practice was compromised to prioritize speed over quality and accuracy. And eventually our descale effectiveness became an issue because of increasing demands from our customers for better surface quality. A major change that happened to this system was that we installed a second descale system that supplied the Pentrol scale breaker, which is the bank of 2 banks of headers right before the finishing mill. So that brought us down to 6 stations for the roughing mill. The commissioning of the Pentrol scale breaker system in 2005 and the startup issues with that system led to a major project that I did in 2010 to improve reliability of that system that earned the 2011 Reliability Achievement Silver Award. So lessons learned from the Pentrol scale breaker system were applied to improving the roughing mill descale system, which is the subject of this presentation. So this project is really a long list of consistent and persistent work. This presentation is put together in a chronological order to describe that work. And the work really started in 2008 and continues until today. So it's important to note that the Reliability Achievement Award process from AIST recognizes that vendors and suppliers are very important partners in improving reliability and sustainability. So in 2008, we added instrumentation to discover that our incoming filter, which hadn't really operated for a long time, was partially plugged and restricting water at a large pressure drop to the inlet of the pumps. So we replaced it with a Ball & Kirk self-cleaning filter with 500 micron filtration. And our bypass line had been around the filter had been too small, so we increased it to the proper size to supply our pumps. During the same period, we also inspected and recertified our 2,000-gallon air over water accumulator to provide some instantaneous flow and some shock absorption. BOC Water Hydraulics helped us with the automatic shutoff valve and instrumentation so we could monitor the level and pressure in our bottle. There's a picture of our self-cleaning filter with our now properly sized piping. 2009, we upgraded our descale nozzles from, by all accounts, had either been in service and unchanged for 30 to potentially 50 years, and upgraded those nozzles to state of the art. Choosing a new supplier for nozzles was pretty easy. Our plant manager had experience at a previous steel mill with Everloy brand descale nozzles. Those are produced in Japan. Just as a note, Leckler is a German company that makes descale nozzles and spraying systems, makes nozzles that are made here in the United States. Both of those companies are very capable and have products that can perform similar descale work. In my particular case, I didn't get a chance to evaluate them because of the directive from the plant manager. But Everloy also provided laboratory testing and simulations based on our standoff distance, header pressure, and existing flow rates to narrow the field. And those simulations were backed up by the laboratory testing to prove that performance would be as expected. So the nozzle selection in 2009 was based on the 7-inch standoff that we have at our horizontal scale breaker, which is our first roughing mill at 7 inches, and then the R1 through R5 stands. It's actually 9 7/8 inches. That's a typo. It's correct in the table. The impact improved at the larger standoff distance. It was about the same at the 7-inch closer standoff distance, but the quantity that drastically improved was the erosion, which is really a measure of how effective the descale is. The nozzles are tested by Everloy and the other nozzle manufacturers using a pressure transmitter that sweeps across the spray to give a profile, which is the top picture there, and the bottom picture is an indication of the maximum impact pressure is experienced throughout the spray. The laboratory testing sprays a aluminum test plate that reacts similarly to scale on steel. Everloy conducts that test there at the closer distance for about 7 minutes and the farther distance for about 15 minutes. The result is a graph that shows the distribution of the spray pattern. The top graph there is the Everloy nozzle. The bottom graph is the older spraying systems technology. And then the pictures on the bottom show the pattern that was developed on the plate, where the top picture shows a nice even pattern with squared edges. Bottom picture, the older technology, it's a little less clean and clear and kind of tapers off at the edges. And moving along then in 2010, we restored our system relief valve, installed a fixed orifice to control the amount of flow. BOC water hydraulics helped us with that unit. As a side note, I guess, high energy centrifugal pumps, such as my 4-stage Worthington, are very sensitive to low flow conditions and to large changes in flow conditions. A minimum flow requirement is usually specified by the pump manufacturer. That minimum flow or higher must be maintained to support hydraulic balance of the rotor and to prevent thrusting and to make sure that the internals of the pump stay cool. Here's a picture of our unloading valve going through our fixed orifice, the dumbbell unit that's in the vertical piping there. And that dumps into the flume just to give the pumps some additional flow to keep them running smooth and cool during idle times on the mill. In the 2011-2013 timeframe, we reconfigured the pump bypass to eliminate the shutoff valve. What we had found was that the weaker pumps that were being shut off, had their bypass shut off, were essentially deadheaded since they weren't able to flow through the bypass and they weren't able to overcome the discharge check valve. So this would lead to rotor thrusting and premature failure of pump gearbox system. We restored the discharge piping of the pump to the proper 10-inch check valve and piping from the 6-inch that had been installed at the time due to previous failed equipment and budget reasons. The piping couldn't be restored to where it should have been at the time. We also installed a fixed orifice unit from BOC Water Hydraulics in the bypass line to regulate that bypass flow. So I have a picture here in one more slide. So the flow then through the bypass needs to be monitored to show the health of the pump and to show the condition of the fixed orifice plates. And at the time, we didn't have the budget to install a flow meter, but the one was specified and a spool piece was installed in our piping so that later on when we did have the funding to install flow meters, we could. So those flow meters were installed in 2017. So there's a picture of our pump setup with our discharge and bypass. So number one there is the discharge line, which was increased from 6 back to 10, and a new style check valve installed. That's at the number one position there. The number two above that, number two on the screen there is the fixed orifice unit, regulates the bypass flow. So there's always bypass water flowing off the pump so that when the system conditions change, the pump always has somewhere to go to send the water. And then the number three on the right of the screen there is the meg flow meter that helps monitor that process. So in 2016, we improved the header prefill system. We always keep water flowing through our headers so that they're always charged. So when you open up the main valve, you don't have water hammer that could damage the nozzles or the header. the previous units had a large amount of turbulence and regular pipe washout. The BOC stacked orifice design eliminates that turbulence. Since we installed those units in 2016, we have not had any washout in that area. And then based on some conditions and some prior experience, we've learned that we need to change those plates out about every 30 months, which is pretty low maintenance. So here's a picture of our one of our descale valves in the center, and up at the top right, you see the double flanged stacked plate orifice system. So when the plates wear out, we just change the plates. The body is a forged stainless steel body, which has a very long lifespan. 2017, we saw that our pump life had been improved greatly with the system modifications made up to that date, but our performance still lagged our expectations. So at this time, we had a pump that was lagging repeatedly after rebuild by 2 different vendors 4 different times. So we took the pump for a full inspection and engineering analysis to Hydroware in Chicago. Their inspection analysis showed poor rebuild techniques and lost details, especially in the impellers, due to a long history of reverse engineering. So copies of copies lose fidelity and performance. So the impellers had lost their original profiles. The housings have been weld repaired, but the top and bottom casings were not matched to each other. This created steps between the 2 halves that resulted in disruptions in flow patterns and pressure drops. The internal passages have been welded incorrectly, created choke areas, choke points, and this created poor performance as well. It's a picture of one of the techniques that Hydroware used to check the quality of the rebuilds from one half of the pump to the other. So they lay out a gasket, cut out all of the openings and the edges, take that gasket and flip it to the other half of the housing and see how well they match. So every place you see metal that's not covered by gasket is a point where the 2 halves don't match. The other main point they found was that the cutwater, the discharge volute, had actually been welded up about 3 inches higher all the way up to the split line than it should have been. So the cutwater should have ended where the red highlighted line is on this picture. But since it was welded all the way up, it was much smaller diameter and created a choke point, which degraded performance. So the Hydroware engineers and repair specialists were able to correct the housing issues. They used computer models and computational fluid dynamics to redesign our impellers. They manufactured new impellers with proper profiles and oversized diameters. They assembled the pump with the oversized impellers tested, got some results, disassembled, trimmed the impellers to match the performance that we were looking for, reassembled the pump, put it back on the test stand again to prove the performance, and it was as we expected. So each of our 6 pumps were rebuilt in this way to return to original performance, and each pump then was fine-tuned based on the testing since each housing was worn differently. So our average pump life to this point has improved from some cases less than a year to as long as now over 4 years. So each pump disassembly includes an analysis of the failures, and we talk about improvement ideas. So we practice continuous improvement. So the goal is 20,000 hours of operation and 5 years of service. So we're getting there one step at a time. So in 2017 then, once we had our pump restoration completed, it was obvious there were additional opportunities to improve efficiency. Everloy had introduced a new generation of nozzles in 2011. Because of other activities that I'm involved with in the mill, I didn't have any time or really need to evaluate those, but now was a good time to look at that technology. So we found that the new nozzles could increase impact and erosion, at the same operating pressure and flow. So with the increased performance of the rebuilt pumps now, it was possible to actually decrease nozzle flow to the point where we could shut off the fourth pump and just run 3. This table is a little busy, kind of small, but we went through the same simulations and laboratory testing to show impact and erosion could at least be maintained and in some cases improved at lower flow rates. So the result of all of that was that we decreased the flow rate at HSB, which is our first descale station, by 4.5%. Kept that flow a little higher because that's our primary descaler and wanted the flow to sweep away the heavier scale coming out of the furnace. Flow rate was decreased at R1 to R5 by almost 15%. So another benefit was that the decreased flow rates. Remember I mentioned that the flow rates had been increased in the past, but now with the decreased flow rates, we had an improvement in the pressure drop from our main header to our nozzles by roughly 33%. So we decreased our pressure drop by 33%. So that increases the energy imparted at the nozzle to the surface of the slab. Also, our header pressure is increased due to the reduction in flow. So our operating pressure increased from what had been about 1750 PSI in 2009 to now routinely over 1850 PSI, which then also increases the effectiveness of the nozzles again. So I'd like to go through a little bit of nozzle theory, just to kind of prove that pumps are important to a system, but they're not the only part of the system. So this was taken from a paper that you can find online that's cited there. So if you look at kind of the development of the formula for impact pressure, you'll notice that in order of importance, the factors are the distance from the strip or slab, the volume of water that's moving through the nozzle, and the pressure that's applied from the pumping system to get that water to the nozzle. I'm sure many of you have used a pressure washer, and you know the closer you get to the surface you're cleaning, the more effective the cleaning is. Well, this is no different, just on a much larger scale. So the flow rate is essentially a one-to-one relationship with the impact pressure. The distance from the strip could be seen as the square root, or I'm sorry, the square of the distance. So if you were able to cut your distance to the surface in half, you have the potential to increase your impact pressure by a factor of 4. And if you looked at the pressure, which would be the water pressure of your system, is actually under the square root. So it has a much smaller effect in changing your impact pressure. Another example, this is taken from another paper, approximation of the impact of descale nozzles. The quantity on the left is listed here as arbitrary, but the result is that the farther you move away from the surface, that would be the height on the x-axis. The green line is your impact, and it really drops off dramatically as you move away from the surface. Part of that is because of the roughly square to the square of the distance relationship. As you move away from the surface, your spray width and your spray depth both increase, which would be the area that you're spraying. So your force of spray over a larger area would give you a smaller pressure. So benefits, by eliminating a pump and running 3 pumps instead of 4, our energy consumption reduced. Our 1,800 horsepower, which equates to roughly 9,800 megawatt hours per year, and roughly $680,000 per year in electricity. So our pump output pressure is increased due to reduced flow and our improved rebuilds. Now, even though we're operating fewer pumps, we have better performance. Our pump and gearbox life improvement will reduce rebuild and maintenance costs by over $320,000 per year. We haven't had any gearbox issues since we started this process 4 or 5 years ago now. those same gearboxes are still in service. Plus, running fewer pumps leaves us now 2 online spares instead of 1, which spreads out our rebuild costs. Our total annual savings are expected to be over $1 million a year. Major takeaways I'd like to leave you with today is that the pump is part of the overall system, but the system dictates how well the pump will run or if it will fail. I like to say the Descale magic happens at the nozzles. The nozzles set the flow rates, which really dictates where your pump is going to operate. So the Descale nozzles have to do the job of cleaning the strip, and you have to choose nozzles based on where your pumps want to operate most efficiently. System pressure is important to get the water to the nozzle, but the flow sweeps the scale away, and the distance from the surface is really the most critical of the 3 factors. Increasing pump pressure has the lowest chance of improving the process and highest chance of degrading reliability. Many of the issues that we found in our Pentrol scale breaker turned out to be pressure fatigue failures. The pressure was too high for the piping network as it was installed and led to rapid fatigue and failure. So higher pressure is not always a good thing. Increasing the effectiveness is really something that should be investigated. So thank you for your time. And my contact information is there, and I understand we might have a question and answer after the presentation. Thank you.
Thank you, Jason. Right now, there are no questions. Like I said, if you do have anything, type it in the Q&A section. And if you do think of something later while Richard's speaking, you can still ask it. And if Jason's still on, he can answer. If not, we will send him these questions for him to answer. Okay, thank you, Jason. Our next presenter is Richard Thomas. Richard is currently the day electrical at the EAF at the new Steel Dynamics Greenfield site in Sinton, Texas for the past 1.5 years. Previously, he was the day shift electrical at the Columbus, Mississippi plant where this award-winning project occurred. He was there for 13.5 years, even back when it was Severcore and Severstal. Prior to Steel Dynamics, he was an aviation technician at Eurocopters in Columbus, Mississippi. Welcome, Richard.
How's everybody doing today?
Good.
All right. Share my screen. All right. So the project that we initiated was at the ladle wall for the preheaters. The initial setup was with thermocouples that have been done that way for many years, and we decided to do something different. So the driving factor at the start of the project is we were constantly changing out the thermocouples, doing unnecessary work to them. There were multiple safety issues because there was always hot ladles going over the ladle wall. The ladle wall itself was 1,800 degrees. The thermocouples were Inconel clad, so we had to cut them off with a grinder. So it was just continuous safety issues involved in that project. Plus then we had ladle walls down, so we were changing out, or we would impact production issues with the downed equipment. We were taking a long time to change out a thermocouple because we were constantly running in and out with the ladles on adjacent walls, moving in and out with the process. So I figured there had to be a better way to do it. In 2017, I went to an automation fair in Atlanta, saw these optical pyrometers sitting on a table, asked them if it would do what I wanted, and of course they said it will, like any good salesman would do. Brought it back to my boss, who told me, yeah, if I think I can make it work, then go for it. So that's how it all started. So I got with Andre Gross and the Advanced Energy team, and we picked out the Onyx S pyrometer. The reason that we went with this particular pyrometer after looking at several different types is that we could actually change the setup in the pyrometer and adapt the settings to the exact emissivity of the refractory material. The emissivity is the ability of any object to give off light when it's heated. So by being able to tune that, we were able to get a very accurate reading. One of the major additions to the project was designing the sight tube for the pyrometer to look through, because the pyrometer is actually looking at the glow coming off the brick, so it has to be able to see through the wall. The hardest thing I had in the whole project was convincing the refractory supervisor to let me cut a 3-inch hole in his ladle wall. So we made the tubes out of a solid stainless round stock, had them turned down in a single piece 3-inch diameter with an 1.5-inch ID and a 5-inch flange on the outside. The tube was then welded in to the ladle wall, and the pyrometer was connected via a bolt pattern, 4-bolt pattern that you see right here. Like I said, we machined it out of 3/16 round stock. It had a 3/4-inch sidewall, so it didn't warp in the 1800-degree continuous heat. Also designed it to where the end of the tube did not stick out of the refractory. One of the things that took the thermocouples out all the time is they had to stick out into the ladle area. So when a crane would pick up a ladle, a lot of times it would hit the thermocouples and bend them. So by keeping the sight tube inside the refractory, we got rid of that problem. We put a sight glass in the tube that was designed for a high temp application, and designed a coin slot into the tube, so it was an easy, quick change. By just removing a set screw, we could take out the old glass, pop a new one in without ever shutting down the process. But we had to push plate the thumb screw that held the glass in. So the first time we were taking we put the pyrometers in, but we were just observing. We had the thermocouple still controlling as it always had, and we were monitoring the pyrometer. So we had the pyrometer set pointing at the bottom of the ladle. I was reading 1800 degrees on the thermocouple, which was our standard set point. The pyrometer was reading 2100 degrees, which we just assumed being at the bottom of the ladle was always a little bit hotter, wasn't a problem. And we watched that for several days and it stayed consistent. So once we got satisfied that the pyrometer was working properly, we decided to attempt control with it. When we started, because I was always seeing consistently 2100 degrees at the bottom, that's where we put our new set point on the burner controller, was at 2100 degrees. The thermocouple was still in. Now we were monitoring it, and it was showing 1800 degrees like it always did. Everything looked good. Looked like we had a good application going on. The shop was running wide at the time, which means we were cycling ladles through the ladle wall every half hour or so, or less. Then one morning I got a call, said the ladle was overheating. I go down there, take a look at it, and the sight glass had coated over with slag, and there was almost no light getting through. So the pyrometer is seeing the light. If it can't see the light, then it's not going to get a good reading. So the burner was maxed out all the way open because it was trying to reach that set point. So we were overheating the ladles. So changed out the glass, everything went back to normal. It was all good. Problem was, this kept happening. We changed the glass over and over and over again. Now, instead of being down there changing thermocouples, we were down there every day changing out the sight glass. So that was the problem we had to solve. Now, once the shop slowed down a little bit, we started running a narrow product. The ladles are sitting on the wall longer. All of a sudden, that 2100 degrees was now reaching the thermocouple, soaking in the entire ladle. We were overheating the ladles. Actually, at that point, we were melting the slag out of the ladles. So we had a problem. At that point, we called that trial number 1, and it was a complete failure at this point. We couldn't get stable control. Stepped back, thought about it a little bit, decided to try it again. Trial number 2, we took a few different measures. So we used the same sight tube, same pyrometer. We added an air purge to keep the sight glass clean, which did absolute wonders. We also changed the target location. We decided to get an average temperature that we could hit either a 9 o'clock position or a 3 o'clock position in the ladle. And that would probably be our best average temperature in the ladle. The thermocouple was back in control again. The pyrometers are back monitoring. We started another trial. This time, with the pyrometer pointing at the 9 o'clock position in the ladle, it was showing 1800 degrees, just like the thermocouple was. So you can see in this picture, the trial number 1 sight tube down here at the bottom. You can see how it was recessed in, but it was pointing straight into the bottom of the ladle. The sight tube on number 2, we did the calculations and we've got it pointing towards exactly halfway down the ladle, which our ladles were 16 foot deep. So it's pointing at 8 foot down at the 9 o'clock position. So this gave us the best average temperature inside the ladle. To do that, we designed a wedge adapter that welded onto the ladle wall, and then the sight tube bolted onto that. This is what ensured our proper angle. So we started observing our controlled test. The pyrometer was showing the ladle actually coming off the caster already over 1800 degrees. The thermocouple, while it was still in control, was increasing the burner to full open to bring the temperature on up because it couldn't see the 1800 degrees because it's such a lagging indicator. The pyrometer was showing the ladle brick overheating. At some point in time, getting up to 2500 degrees before the thermocouple would finally reach that 1800 degree set point and back the burner off and cool everything off. So at this point, got to thinking about it, we could be wasting gas. And we're probably having extra brick wear and damage because of all of the thermal cycling and the extra heat we're putting into it. We're also seeing a whole lot of extra movement on the actuators because with the thermocouple, it's constantly cycling, trying to find that temperature. So now we put the pyrometer in control again. We're still seeing a good 1800 degrees all the time. So now what happened when the ladle came off the caster, the pyrometer was showing 1800 degrees or over, showing real temperature immediately. So the burner stayed in idle fire. It only ramped up slightly when it needed to maintain that 1800 degrees and just keep bumping it. So our mechanical cycling on the actuators went down to almost nothing. sight glass was now staying clean because the air purge we had going through it. And the air purge was designed to sweep right across the glass and then blow out into the ladle. At this point in time, we have achieved a stable control. Everything was running well. Everything looked great. And we let it run that way for a couple of months with just one ladle installed. After we decided that everything looked good, I went back. I had to add another pyrometer to the same wall because the NFPA rules require a completely separate over temp shutoff. So if one fails, the other one will shut the burner off so we don't have a runaway. So we put the second thermocouple in. We pointed it at the 3 o'clock position, directly opposite from the first one. It didn't have any control. It was strictly just to shut down the burner. I did see a little bit of an issue on that one with a splatter on the sight glass. And that was from cleaning out the nozzles on the bottom of the ladle. We ran both pyrometers there together for several months before deciding to proceed with the final installation. On the final installation, which was in November of 2018, we installed the control pyrometer and the high temp pyrometer on the other 4 remaining walls. We also added the Ethernet IP option so that we could tie it into our level 2 system and be able to track the temperature of the ladles coming off the wall for future applications. So as you can see, the control sight tube pointing at the 9 o'clock position. You can see the high temp shutoff sight tube pointing at the 3 o'clock position. Down here below the high temp sight tube, you can see the original old thermocouples sticking out of this wall. Of course, this wall is without the refractory applied, so you can see everything. Just close up with the sight tube coming through. You can see the thick wall on it that guaranteed that that sight tube would never warp. Here's the back of the ladle wall, showing your control pyrometer on the left, your high temp pyrometer on the right. On the control panel right there, you see the 2 burner controllers. We did have to change these out too because the original controllers would only accept the thermocouple input, not the 4 to 20 milliamp. Here's inside the panel, the Ethernet IP communication modules that we installed. You see a close up here, once the refractory is applied to the wall, you can see the sight tube is recessed several inches within the refractory. So when the ladle did hit the wall, which did happen occasionally, it would hit the refractory and our sight tube was always protected. Even once the refractory started wearing down, the sight tube was still inside the wall by the time that they decided to replace the refractory. After several months, we had several observations here. Number one, we had to go down and clean the sight glass a couple of times. Mostly that was dirt on the outside of the glass, not on the inside now. We had a little bit of slag splatter on the high temp sight glass. Again, I said due to cleaning out the nozzle. Doing this project again, looking back at it, I probably put the high temp looking at the exact same location on the 9 o'clock position as we did the control pyrometer, and that would alleviate that situation. I had one minor issue of plugging in the sight tubes. Actually discovered that was refractory sprayed into the tube. It wasn't actually sealing over on its own. I did have to replace 2 pyrometers since we did the installation. One of them was actually a manufacturing issue. We had to swap it out under warranty. The other one, we tried running without the sight glass installed, and that was a bad idea. It ended up burning up the pyrometer. So, operations and maintenance both liked the new systems. Maintenance liked it because they didn't have to go work on it all the time. Operations liked it because it was giving them a lot more stable control. And their ladle walls had a much greater uptime. We had a lot smoother operation on the actuators and the valves, and we saw a lot less gas usage. So we went from every other day trying to replace thermocouples to virtually zero maintenance, getting called down there once or twice in 6 or 8 months. We had a faster response time because that went from a lagging thermocouple indication to an instant indication because we were looking at the glow of the brick. We had less wear and tear on the equipment because the actuators are hardly moving now. We're using a lot less gas. We're saving a lot of money because we're not replacing the equipment all the time. In addition to the gas savings. With the gas savings, that also reduced the company's carbon footprint fairly significantly. The cons to the project, because of adjusting the emissivity set points inside the pyrometer, we cannot see a temperature lower than 1430 degrees. The only time that this really comes into play is during an outage when we let all the ladles get cold. Then we have to put a temporary thermocouple back in place just to get the ladle up to temp so we can bring it up slow. Any other time the ladles landed on the ladle wall are either coming from the process, from the caster, or they come directly off the vertical preheater, so they're already at temp. So the operations guys, the shift guys wanted to keep it. They didn't want to let me take it out. But I want to go back and look at the financials of it as well. So to build this project over about a 2-year process, spent $57,000 in electronics, hardware, and cables. The site tube, R&D, and machining and installation for all 5 walls cost me $21,750. The air purge, the hoses, regulators, all the fittings and everything was another $1,500. So we're just over $80,000 to complete the entire project, R&D and final installation. Out of that, well, our natural gas savings, we started tracking for 4 months after we installed the projects, and we saw significant savings in our overall natural gas usage. You will notice in June that there was actually a negative value thrown in there that kind of messed up my good numbers. But the reason that one was negative is because the ladle wall is counterintuitive to what you would think in gas usage. When the shop is running really hard, like we were in March, April, and May, we actually use less gas because the ladles don't sit on the wall as long. In June, the shop slowed way down in June of 2019. So we actually had to use more gas because the ladle sat on the wall longer. Even with that said, we calculated it out on the average per month, and we were saving about 5 million cubic feet per year of natural gas. So projected savings of $65,458 at the current price of gas at the time. So our return on our investment, we were saving over $21,000 in thermocouple replacements a year. The labor to replace those thermocouples is almost $5,000 a year. $65,000 for natural gas. Take away the $80,000 that I spent to do the project. The first year we saved $11,500. Every year after that, we're saving at least $91,000, almost $92,000 a year. The project had an instantaneous return of 239% with a payback period of only 11 months. So the project was a great success. Talked to the guys in Columbus the other day, even though I'm not there. They're still loving it. They're bragging on it. Everything was working great. So that's the end of the presentation that I have.
Okay, thank you, Richard. I don't see any questions right now. We'll give people another minute if they wanted to write anything. Okay, well, I appreciate everybody's participation, and thank you, Richard and Jason, for coming on and displaying your project. Again, we have their emails and contact. If anybody thinks of anything later and would like to write to them, you can either do it directly or please write it to me and I'll get it to them. All right, thanks so much, everybody.
Thank you.
All right, have a good day. Bye-bye.
Okay.